Welcome to part 2 of my playlist about the best methods to convert aliphatic alcohols into chlorides. This presentation is about the use of thionyl chloride as deoxychlorinating reagent. Thionyl chloride is inexpensive and safer to handle than phosgene solutions because it is a strongly irritating lacrimator, what prevents longer inadvertent exposure. Thionyl chloride is prepared on a large scale as deoxychlorinating and dehydrating reagent and as cathode for certain types of lithium batteries. One process consists in the gas phase chlorination of mixtures of sulfur dioxide and sulfur monochloride, but sulfur trioxide or sulfur dichloride can also be used as starting materials. Thionyl chloride is not very stable and decomposes slowly at reflux temperature into sulfur monochloride, chlorine, and sulfur dioxide. Upon reaction with thionyl chloride, alcohols are first converted into chlorosulfonates, which can decompose into alkyl chlorides and sulfur dioxide in a variety of ways. Interestingly, thionyl chloride often brings about the transformation of secondary alcohols to chlorides with retention of configuration. It is assumed that this so-called SNI reaction, I for internal, proceeds via a tight ion pair, from which the ions do not diffuse away, despite the absence of covalent bonds. This is, however, not always the case, and many thionyl chloride-mediated deoxychlorinations proceed with inversion of configuration. Thionyl chloride can convert alcohols into chlorides both under acidic and under basic reaction conditions. Under acidic conditions, the same limitations as for the use of hydrogen chloride apply, and the solvent should be as acid-resistant as possible. Chlorinated alkanes or an excess of thionyl chloride are common solvents, while ethers, esters, nitriles or ketones are less well suited, because these can react with thionyl chloride. I'll discuss some of these reactions later. Deoxychlorinations by thionyl chloride can, however, also occur under basic or almost neutral reaction conditions, for instance in the presence of a slight excess of pyridine. These milder conditions allow for a broader selection of solvents. To prevent the accumulation of thionyl chloride in the reaction mixture, for large-scale preparations, the use of a catalyst and the dosing of thionyl chloride at slightly elevated temperature may be the safest way to conduct this reaction. Suitable catalysts include DMF or other amides or ureas, or Lewis acids such as titanium tetrachloride or zinc chloride. In this example, the amino alcohol was added dropwise to a slight excess of cold thionyl chloride, without any additional solvent. Despite the formation of salts, the reaction mixture remained stirrable and a good yield of alkyl chloride was obtained. In this example, an acid-labile reactive benzylic alcohol was deoxychlorinated with thionyl chloride in the presence of pyridine to prevent acid-mediated cleavage of the Boc group. Because of the high reactivity of the starting alcohol, the reaction could be run at room temperature and was complete after 3 hours. Much less reactive than donor-substituted benzylic alcohols are neopentylic alcohols, such as pentaerythritol. Nucleophilic substitutions at neopentylic positions are difficult, and a high temperature was required for the deoxychlorination of pentaerythritol. The target product of the synthesis was the trichloride, and therefore only 3 equivalents of thionyl chloride were used. The use of pyridine in these reactions renders the reaction mixture much less acidic than without any base, but pyridine hydrochloride is still a rather strong acid. Methoxyarenes, for instance, can be cleaved by heating with pyridine hydrochloride. Thus, if one's starting material is very acid-sensitive, a stronger base than pyridine should be used, for instance N-methylimidazole or N-methylmorpholine. This procedure was optimized to be performed on a large scale. Thionyl chloride was added slowly and DMF was used as catalyst to prevent the accumulation of thionyl chloride in the reaction mixture. Only about 0.6 equivalents of thionyl chloride were sufficient to convert each hydroxyl group into chloride, and no formation of the cyclic ether was observed. The reaction was conducted in toluene, despite the low solubility of most salts in this solvent. deoxychlorinations with DMF probably proceed by intermediate formation of iminium chlorides, which are discussed thoroughly in part 5 of this video playlist. These examples show how the stereochemical outcome of the thermal decomposition of chlorosulfonates is impacted by the choice of solvent. In this instance, retention only occurred in dioxane as solvent, whereas in apolar, non-coordinating isooctane or without solvent, the configuration was mostly inverted. These results suggest that in the case of dioxane, an oxonium cation was formed as intermediate by O-alkylation of dioxane, followed by a second SN2 reaction with chloride. In this optimized procedure, no solvent, but only a catalytic amount of tetraalkyl ammonium chloride was used to promote the thermal desulfonylation of the chlorosulfonate of methyl lactate. The product was distilled off as it was formed with complete inversion of configuration. Alpha chloroesters, such as the product of this reaction, can be racemized by heating in the presence of chloride, and it is therefore important to remove the product quickly from the reaction mixture if its optical purity is to be preserved. An example of chloride-induced racemization is given in the phosgene presentation of this playlist. Now, what are the potential side reactions? When chlorosulfonates are prepared without base, HCl is formed and the reaction mixture turns strongly acidic. Under such conditions, the same side reactions can happen as with hydrogen chloride, for instance, rearrangement of carbocations, isomerization of alkylarenes, and the addition of HCl to olefins. Alcohols with heteroatoms in beta position can also yield isomerized products by intermediate formation of three-membered cyclic cations. In the example on this slide, bromide migrated and a benzylic chloride instead of a primary chloride was formed. In this example, a chlorosulfonate was desulfonylated at low temperature by treatment with 10% of titanium tetrachloride. Despite the mild conditions, still 2% of hydride migration occurred. Cyclohexyl derivatives, however, undergo elimination and hydride migration particularly easily. In this example, a sterically demanding benzylic alcohol was treated with thionyl chloride. At room temperature, the expected benzylic chloride was formed in good yield, but at reflux temperature, the starting alcohol underwent dealkylation and cyclization to an indane. With an excess of alcohol, sulfides instead of alkyl chlorides can result. These are stable compounds that do not readily undergo substitution reactions. Sulfide formation can become an issue if the alcohol is too unreactive or if the reaction temperature is too low. Intramolecular reactions usually proceed much faster than intermolecular reactions, and when 1,2-diols are treated with thionyl chloride, cyclic sulfides are readily formed. In this example, despite the excess of thionyl chloride and the high reaction temperature, a good yield of the cyclic sulfide was obtained. Also, amino alcohols and enolysable hydroxyketones can be converted into cyclic products by thionyl chloride, as shown here. In this case, the resulting sulfamidite was oxidized to cyclic sulfamate, which acted as electrophilic benzylating reagent. One further potential side reaction is the electrophilic sulfonylation of CH acidic compounds. In this instance, treatment of the starting acid with a large excess of thionyl chloride led to a strongly CH acidic alpha-pyridinium acetyl chloride, which underwent clean sulfonylation at carbon. Malonic esters can also react this way. More often than sulfonylation, CH acidic compounds undergo chlorination or thiolation, as shown here. Methyl ketones, 2-methylpyridines or 1,3-dicarbonyl compounds can all be oxidized by thionyl chloride, often at surprisingly low temperature. For this reason, ketones such as acetophenone or acetone are not well suited as solvents for reactions with thionyl chloride. In this example, malonic acid was chlorinated by treatment with 1.9 equivalents of thionyl chloride. Despite the free carboxyl groups and the use of acetic acid as solvent, acyl chloride formation was much slower than the oxidative chlorination reaction. Also electron-rich olefins, arenes, and heteroarenes can be chlorinated or thiolated by thionyl chloride. Cinnamic acids, for instance, can be converted into chlorinated benzothiophene when heated strongly with thionyl chloride. And in the presence of light, thionyl chloride can yield chlorine radicals and cause radical chain chlorinations of simple alkanes. Even electron-deficient olefins can sometimes be chlorinated by thionyl chloride, as shown here. Instead of the expected acyl chloride, treatment of acetylene dicarboxylic acid with an excess of thionyl chloride at 40 degrees Celsius gave mainly dichloromaleic anhydride. This here is an example of the sulfinylation and thiolation of anisole by thionyl chloride. The product ratio could be influenced by the choice of Lewis acid catalyst. Thionyl chloride can also oxidize pyridine to a dimeric pyridinium salt. Because pyridine is often used as a solvent or base for reactions with thionyl chloride, this pyridinium salt is a potential byproduct of such reactions. Also DMF is often used as catalyst for thionyl chloride mediated deoxychlorinations. It has been found that thionyl chloride can convert DMF into dimethyl carbamoyl chloride, a known human carcinogen. Carbamoyl chlorides are much less reactive than acyl chlorides and remain largely unhydrolyzed and in the organic phase during aqueous workups with toluene or dichloromethane. Thus, this byproduct may find its way into the final product of a synthesis. Here are some further examples, but many more have been reported. The next presentation is about phosgene as deoxychlorinating reagent. Phosgene does not generate any sulfur or phosphorus waste and is therefore often the reagent of choice for large-scale deoxychlorinations.